Alright, this is just an introduction to Riemann sums. Riemann sums is the correct way to spell it. Here's the basic idea. If we have some graph and we wanted to find the area underneath that curve and between that curve basically and the x-axis, we can estimate that area by putting a series of rectangles underneath it. So let me give you a quick little example here. And we're using x squared there below, so let's just use the graph of y equals x squared. And let's just go to we'll just say this is 2. Well, there's some area in here. Well, we can estimate that area by putting a bunch of rectangles underneath it. And there's a lot of different types of rectangles that we could put under there. We list a few of them here. We could use right rectangle approximation, left rectangle approximations. We could actually use trapezoid, and the other one is a midpoint rectangle approximation method. For now, I'm just going to show you right rectangles because that's what we're going to start off with anyway. So when they say right rectangle, all that means is that the rectangle touches the graph on the right side. So let's say I was going to put in 2 rectangles here. There's one where the rectangle touches the graph on the right side. And there's the second rectangle. And so what I could do here is I could essentially find the area of these 2 rectangles because, well, this would, we're actually going to call this delta x because it's the change in x. In this situation, our delta x is just 1. And then we're going to find the height here. And you could find the height because this, like I said, this graph here is just y equals x squared. And so you could find the height. The height is just the height at 1. So this first rectangle would just be, the area of this first rectangle would be 1 times 1. Plus the second rectangle, again, that's just a distance of 1, so it would be 1 times a height. Well, the height here is just y of 2. Well, that'd be 2 squared, so that'd be 4, so this is 1 by 4. And so we get that the area of these rectangles would be 1 plus 4, so not approximately, it would be equal to 5. And so this 5 is an approximation for the area underneath this curve. So you could see how you could get kind of close to the area, at least an approximation. And the more rectangles you put underneath there, obviously the closer this approximation will get. And the different types of rectangles will change the approximation. You can kind of tell right here that this is an over approximation because the rectangles are going above the graph. And if we were to do the same thing, I'll just sketch it real quick. With a left rectangular approximation, that would mean that it touches at the left point. So the first rectangle would actually have a height of 0, and the second one would have a height of 1. And so this one would be 0, this would have an area of 0, and this one would be 1 by 1, so this would have an area of 1. It's a plus 1. So this left, this is, I'm going to say L ram. And over here, this is R ram. The left rectangle approximation is an under approximation, right? So we know it's somewhere between 1 and 5. And the more rectangles we use, the closer we'll get to the true area underneath that curve. So that's the basic idea of Riemann sums. So let's talk about some of those different concepts here. Like I said, you got the right rectangle, see how it touches on the right side of the rectangle or the left side of the rectangle. We also could fit trapezoids in there. Trapezoids fit kind of nicely. However, if it's important thing to know about trapezoids, and this isn't a great diagram of it. So if we make a little bit better one, we could kind of see something. If you have a curve that concaves up, and you were to put a trapezoid in there, right, that is still going to be a slight over approximation. But if the curve is concave down, now a trapezoid would be a slight under approximation. So something to consider as you're thinking about how a trapezoid approximates the curve. Is it over or under? Well, it just depends on whether it's concave up or down. Same thing's true with LRAM and RRAM. This RRAM is only an over because it's concave up, and this is because it's concave down. As soon as you change the concavity, so we could kind of see like a quick sketch of something like this. And if I was to put in a right rectangle, you could now see that this rectangle, even though it touches on the right side, is now an under approximation. And if over here as to put in the left rectangle, now the left is an over an approximation. So it all just depends on concavity. It's a good idea to kind of sketch it out and see whether it's over or under. All right, that's probably a lot more than we need about Riemann sums for right now, but let's go on the next page. So a little bit more about it. Remember, we got circumscribed rectangles. This just means these rectangles, again, these are just drawings with one rectangle in there, but we're going to put many in there. And they're just touching it at key spots so that we can calculate the height and the width of these rectangles and add up all those areas and approximate the area underneath that curve. That's really all it is. So, yeah, if it's circumscribed, that means that it's an over approximation. We could see here that both LRAM and RRAM could be over approximations depending on the curve. These are inscribed, and these are going to be an under approximation or a lower sum. So you could see that it's not going to be, it's going to be a little bit less than the actual area underneath the curve. Here we have some different ideas here on how a right and a left would look and how it's an over and under. So a lot of little different examples here. All right, and let's go to the last, because we're going to talk about delta x. And remember, delta x is, you know, if I was to put in, I'll just do a basic curve here. If I was to be putting in several rectangles, let's say this is 2, that would mean this is 1, and I was going to put, we'll do the rectangles in blue. If I was going to put in 4 rectangles, let's say, and I'm just doing some, sketching some right-hand rectangles here. Well, this first one is actually a height of 0. I should have drawn it just as a straight line. But basically what you have here, the delta x is this distance here. It's like the base of those rectangles. It's just the width. And usually we're going to have the same width on all of these rectangles. And so we can calculate that pretty easily. Like in this one, you could calculate the width by doing 2 minus 0. That gives you the total distance, or b minus a, because you're going from 0 to 2. So b minus a, and then divide by the number of rectangles. So in this situation here, the width, we can tell by looking at it, it's going to be 1/2, and we could use this little formula to see 2 minus 0 divided by 4 equals 2/4, or 1/2. Okay, so that's the delta x. So I just want to practice calculating the delta x here real quick, because this is something that's going to need to be somewhat routine for us. So as we look at this first problem here, remember it's just b minus a over n. Well, this interval tells you your a and your b. We're going from 0 to 4, and n is the number of rectangles. So this is 4 minus 0 over n. And our n is 4, so let me just change that to a 4. So you get 4 over 4 equals 1. So your delta x is 1. That's it. Okay, so when they ask for the delta x, it's just this simple formula. Let's do the next one. So it's going to be 4 minus 2 over n. The n here is 3. So the delta x is 4 minus 2 over 3, so that's 2 over 3. That's it. That's your delta x. I think you should be able to find the delta x for this last problem. Go ahead and give it a try, and then check back in just a second and see if you did it correct. All right, the b here is 4, and the a is -4, so 4 minus -4, that's a double negative, so it turns into a plus. And the number of rectangles is 4, so 4 plus 4 is 8 over 4, 8 divided by 4 is 2, so your delta x here is 2. Real simple. Basically, all we're doing is just calculating the width of these rectangles. All right, see you guys in the next video.